Welcome to Ask and Learn.
So once again, welcome to a new problem, and think about a material, and you can have a material such as a metal, and on the metal you can aim a laser on it, and obviously the laser is producing a beam, and these are high intensity beams, and these beams are continuous and they produce light, and each of the pulses has energy in it, and the energy in the pulses is equivalent to 500 millijoules, and of course the time it takes to produce this pulse is about 10 nanoseconds. Assume that we have 10 pulses coming off of this laser, and we want to go ahead and figure out a couple of things about this pulses. So we want to first of all find the maximum power of the laser light, or what you can call the peak of the laser light, and the peak happens within these 10 pulses. So it's going to happen within 10 nanoseconds. So that's what we're looking for in the first part of the problem. And then the second part of the problem, we're still looking at the power output. Remember, you have multiple pulses, and out of these pulses, you're saying we want to get the average. So you want to get the average power, because you're getting a bunch, 10 pulses, and you can average them out. So we want to get the average power that these pulses are producing. Remember, power is defined in joules per second, or the energy per unit second. And then the other thing we were saying is, assume you have a surface right there, and then you have the beam coming in, and before the beam gets to the surface, you have a lens. So this is a lens, and the lens is going to focus the light. So you have all this beam. Maybe we can make it a little bit bigger than it is right now for purposes of understanding the problem. So we have a laser right here. It's a little bit wider than you're seeing. So we have a laser beam coming in, and once it gets to the lens, it doesn't always go in with the same diameter. So what the lens does, it changes the orientation, such that right now we have a new focus, and this diameter is 10 micrometers in terms of intensity. And then finally, we also want to figure out the couple of things. We know that the intensity of sunlight, I'd say around about 12 noon, is give or take 1,100 watts per meter squared. So our goal is to figure out the ratio of the intensity of the laser relative to the intensity of the sunlight. So those are a couple of things we want to figure out. So just to clarify the requirements of the problem, we want to get the peak power, the maximum power out of all these pulses. We also want to get the average power of all these pulses, and we also want to get the diameter. So we want to get that. And also we want to get the ratios of the intensity between the laser beam and the intensity of the sunlight. So those are issues we're looking at. So in the first part of the problem is the peak is going to happen during a single pulse. That's when the peak is going to happen. The average, on the other hand, is going to happen where we have the total energy per unit time, and that's in joules and seconds, as you're seeing. This is the average power, and this is the peak power. Those are things we're looking at. And the intensity, by definition, the intensity, if you're defining the intensity, you're defining it as the power per pulse relative to the area that you're looking at. So these are just notes to help you understand the meaning of all these things that we're going to be resolving. So in part A, we want to get the peak power, and that's the power output per unit pulse. So power output, so the energy per unit time, that's 500 megajoules relative to 10 nanoseconds, and we have to transform this to SI units, so 500 times, actually it's not megajoules, but it's millijoules. So this is just for your own understanding, this is millijoules, and this is nanoseconds. This is nanoseconds, so you want to be comfortable with that. So this is 10 to the 3 joules. We've made the transformation, or actually 10 to the negative 3 joules, because it's milli. And then we have 10 nanoseconds, so that's 10 to the negative 9. We want to make sure that this is 1, just to be comfortable with the requirements. Seconds, 10 nanoseconds, it's actually 10. So when we simplify that, we end up getting the same thing as 500 times 10 to the 5 watts, and we want to change that to manageable units. So peak power becomes the same as 5 times 10 to the 7 watts. 5 times 10 to the 7 watts. That's the peak power that we're dealing with. The next thing we want to resolve is the average power, and that's simply the same as the total energy, relative to the time, the total energy relative to the time it takes. So we got the peak power. Now we're talking about the average power. So this is the same as 500 millijoules and times 10 nanoseconds, and that becomes 5,000 millijoules, which is exactly the same as 5 watts. That's exactly the same as 5 watts. So the next thing we're looking at is the intensity. Now we're dealing with the intensity, and we define that as the power per unit pulse relative to the area that you cover. So power per unit pulse relative to the area that's covered. And the power per unit pulse, that's the peak power. And over the area, we already resolved the peak power. If you go back, you see it's 5 times 10 to the 7 or 50 times 10 to the 6. So we end up having 50 times 10 to the 6 watts per meter squared. And then we do actually watts. This is at the top, the numerator. That's the numerator, that's watts. And then the area, we have to figure out the area we're dealing with. Remember, the diameter is 10 micrometers. So the radius is half of that, so 5 micrometers, which is the same as 5 times 10 to the negative 6 meters. And the area of a circle is pi r squared, which is the same as pi times the radius squared. And so that area is going to be 78.54 times 10 to the negative 12 meters squared. And if we simplify this, we end up having the intensity of the laser beam being the same as 0.64 times 10 to the 18 watts per meter squared. That's the intensity. The next thing, or the final thing we're looking at, is the ratios. And these are two ratios. The first one being the ratio of the intensity of the laser beam relative to the intensity of the sunlight. We already have the intensity of the laser beam, and we had it as 0.64 times 10 to the 18 watts per meter squared. And then the intensity of the sunlight was, if you go back up, was 1100 watts per meter squared. So that's the one we're going to be using, watts per meter squared. And if we simplify this, we end up with 5.82 times 10 to the 14. That's the ratio. That's the ratio. If you look at these intensities, we're getting specific ratios. So, if we have 0.64 divided by 1100, that's 5.82 times 10 to the 14. That's the ratio of the laser beam that we're dealing with. So that's kind of how you simplify this problem. And the 0.64, this is a rounding off, times 10 to the 18. So once again, we had a problem. We had to resolve a couple of things with this problem. The first thing is to get the peak power, which is just the energy over the time, and that's in joules per second, 5 times 10 to the 7 watts. And then we had to resolve the total energy relative to the time, and that's going to give us 5 watts, the average power. Okay. The average power is total energy relative to the time. And then finally we have the intensity. We first of all find the intensity of the laser beam, which is the total peak power relative to the area. We need to use pi r squared to resolve the area, and then we get the intensity of the laser. And then finally we have 5.82 times 10 to the 14, which is the ratio that we're looking at. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.